Hello.
Hello, Sagar.
So are we going to start 3.6?
We'll see if, we can make it today or not. Not sure. Probably yes. What's 3.6? I have no idea what 3.6 is. Second order? We talked about second order equation before, actually. That's weird. We did talk about 3.6 before, so it's covered. Okay, so let's start. Do you have any questions? All right, so first let me address the issue about responders. I'll post a announcement after the class, but so here's the final resolution with responders. So what I'll do is I will post two versions, okay? Two instances of the exam. One with responders and one without. All right. You are required to do the one with responders. So, basically your activities is monitored, right? You must do the one with responders. But after you're done, you can quit responders and then submit on the other one. So in that case, right, in that sense, submit with the other one. After you're done. All right. So that's the basic scheme. So so this way, right? I have monitoring, right, of your test activities, but then you can also submit when you need to. So I won't turn off and turn on that kind of thing. There will be two instances of the test. But right, it's very important that you do the one with responders. If you don't do that, then I will have to kind of contact you somehow and find verify your activity in some other way, which may be more involved. Any question on this? So no, right? I mean, well, roughly yes and no. So first, the test you can access it 5 minutes prior, right? Like last time, so 4:55, things will open up to you. You have to 6:30, right, to turn in. So as before, so the extra time is meant to account for whatever things you need to do to scan and that kind of thing. Yeah, but highly discouraged. Okay, well. Okay, so that's weird because I think the opening file, some people can and some people will still say they can't. So these two versions of the exam, all right, they will both have access to the exam, But I don't know if I want to encourage you to go to the one without open the exam and then open it up or something. So try to see if you can open with the responders one. But in either case, right, the one without will have the exam too. So both exam will end at 6:30. Okay. They have exactly the same format. It's just one with responders, one without. So after you're done, whenever you're done, you turn it off and then you post it. No, both of them are available from 4:55 to 6:30. But right, the responders one will have the record of the activity, and I would like very much to see the activity of your responders most of the time, right? So if you spend only 5 minutes on responders, that kind of is weird. But both of them are available from 4:55 to 6:30. And yeah, the practice exam the practice whatever thing you can access anytime. You can go to the other file, right? You can go to your exam. These two exams are the same thing. You understand? They are one and the same thing, like just two instances. But like one is allow you to submit. Yeah, so Ashim, I think within 15 minutes is reasonable after you close it. Yeah, exactly. That's the point too. Like if you close the responders like 30 minutes before you submit, that's weird. But as long as like there's a reasonable amount of time to transition between one and the other, that's fine. So timestamp is there to verify things. Okay, so again, you should be able to access exam on both versions, but I can't test responders on my side. Okay, I don't know. I mean, I cannot download the test as a student or something. So you figure out what's the most convenient way for you to do so. All right, and I think maybe the most convenient way is to access the file on responders itself. But like some people still say they can't, but I'm sure some people can do it. So play around with it if you want. You can access on both. All right, but I would like to see majority of your activities spent on responders. Any other concerns, questions? I could like simulate this. I could open another instance of the practice exam, without responders. So you can see whatever you want to play with, like simulate the exam for you or something. What issue? I'm not so sure. Like again, I said some people like majority people can open on responders. So I don't know what is that prevents you to do so. Worst case scenario, you just go to the other exam and open the file, and then go back to responders to do the problem. I'm not sure if that will work, but yeah. So you already have a practice quiz with responders, right? I was just gonna post another one. Yeah. Uh, open the exam on that case. Huh. Uh, that's tricky, right? Because it's hard to verify whatever you're doing on the phone. So yeah, it's really annoying. So how do I want to say this, right? Does responders not allow you to open any file on the computer? All right. So here's this. Uh, No, I'm not talking about upload. All right. Okay, here's the deal. The ones who can open the responders, do you mind sharing your open thing for people to see it? I'm gonna open up for people to screen share. If like Carl or Jatin, can you show people? Oh, that's true. That's silly. Oh God, I hate that. That's true. Uh, that's true. That's true. That's a silly thing to ask. Uh, some privacy issue. I don't know. It's university wise. Uh, so okay. So I guess the thing is this, right? Like I said, you have two instances of the exam. So you can always access the exam on the other one. My question is, once you enter responders, can you still keep the exam up for you to look at? No, you cannot. Huh. Um, ugh, I really don't like this. So, okay, here's this, right? So Carl, can you type in the instruction, like what to do? You have a screenshot? Oh, but you can't, right? You cannot even take screenshot, can you? Hmm. So in the file that Param just sent, is there a magnifying glass somewhere in the preview of the document? That thing, right? That preview document, is that the magnifying glass? So when you click on it, param, it doesn't work. It works. All right. Hold on. So let me try to see polls. Add a question. Let me see here. Magnifying class works for you. Oops, sorry. Yeah, don't click on the file. Okay. Okay, I guess. So would people take 5 minutes real quick to check if that option works for them, and whoever left cannot work, like the magnifying glass option? Take 5 minutes and please everyone try to see if it works for you. I just want to have an idea of how big this issue is for how many people. Yeah, leave and try, come back. Yep. Leave and try and then come back and then let me know how many has it and how many doesn't. The practice responders is on the quiz, practice quiz. It says practice responders. Yep. Resend what, Lauren? Yeah. If you cannot launch it, if people who cannot launch the file, if you could launch it, then you're fine. It's always there. So log out and test it to see, right? People say you click in the magnifying glass. So try it. Yeah, cool. Thanks. Technology. It's just crazy. All right, very good. Good to know. Cool. Yeah, so I think it's just people miss that. People click on the link. Yeah, Lauren, uploading is exactly you do it with the other with the other exam. Okay, you upload with the other instance. I'll post two instances. You upload with the other one after you're done. Yeah, roughly. You can start 5 minutes early. So, technically 4:55 to 6:30. Yeah, I can make it 6:35. Doesn't matter to me. Yeah. All right, I think still missing about 9 people. Let's give them like 2 more minutes and then we'll start. So among the 31 here, I guess 30, right? 31 including me. Everyone is okay with opening that file? Is anyone not able to, is anyone not able to open the file? Yeah. Okay, thanks. Cool. I should know how to poll, you guys, but I just click on poll and it doesn't work. I mean, I don't know. I should do better. All right, a few folks who just logged in, you got the file okay? Any issue? Okay. All right, so I can safely assume that it works for majority of the class. Is Param here? Param, are you here? Can I use the picture you sent as a, like, I'm just gonna post it to the class and circle the magnifying glass so people who don't attend the session can, you know what to click on. Seems like that's a little secret. I can't, go into responders myself. Okay, that's fine, right? There's no sensitive information on that picture you don't want to show the world, right? You should try cat. You should try, okay, if you have an issue. Is again, uploading is for that you have a separate instance to upload, okay? But with download, I cannot help you there. download, you should download on the responders itself. Otherwise, like the system won't let you open both at the same time, as people said. So try it with the magnifying glass, make sure it works for yourself. All right. Otherwise, you won't be able to access the exam. Okay, so thank you, Param. So I hope that resolves it. Okay, any other question? Okay, so what else do I want to say? Yep, Param sent a file like here. All right, if you look at that file, there's a magnifying glass right next to the link, and if you click on that, the exam opens up for you. Is that right, everyone? Yeah, all right. So don't click on the link, right? Click on that magnifying glass. All right, so finally I can start discussing math. So what was it, right? So we still were discussing, right, system with repeated, right, eigenvalues. Okay, so let me restart my iPad real quick. All right, sorry, yeah, good stuff. System with repeated eigenvalues. Okay, so hold on. What you need to do there, right, is the case where you're responsible for the case where of eigenvalue with multiplicity 2, okay? This can happen either 2 by 2 or 3 by 3. So today I want to round off my discussion with the multiplicity of 3. But I feel it's really an interesting thing that I want to show, right? I want to discuss for everyone. Otherwise, you are under the impression that things are always this easy. But on the other hand, right, it is a little bit nuanced, so I won't put that on the exam, all right? But here, right, basically, eigenvalue with multiplicity 2 is what you need to know, right? So the case with one pseudo eigenvector is what you need to know, okay? So this always involves one pseudo eigenvector. And for that regard, right, I think for some reason, a lot of people ask for question 5 on the homework. So I want to kind of address that for the class. I'm not so sure what the difficulty is, but I want to do that right for you, so you see what the deal is. So problem 5, you got y prime equals to minus 3, 0, 1, minus 3y. I think the most common question is somehow the form of the solution that I present don't match with the book for some reason, the solution, and then also how to deal with the initial condition, right? So I want to address that. So first, right, here it's pretty clear that the eigenvalues are minus 3, repeating. If you plug in minus 3, right, then you got 0, 0, 1, 0, okay? So if you solve for the first eigenvector, this is the system. And so it's clear that the eigenvector, right, there's only one eigenvector here, which is 0, 1, and then with a free constant in front of it. All right. And so because there's only one eigenvector, right, you need to solve for the pseudo eigenvector. And the pseudo eigenvector will solve, right, this. Yes. So first you find a particular solution. The particular solution would be 1 and 0, right? 1 and 0, ignore the C1, right? 1, 0 would solve this. So with the C1, that would be C1 in front. So this is the particular solution. And then, well, a particular solution, right? And then you need to add the homogeneous solution, which comes from the eigenvector itself, which gives you C2, 0, 1. So this is V2. This is the pseudo eigenvector. All right. Any question here about this process? So part A for the general solution would give you the answer like this. So my answer would be, right, that the pseudo eigenvector times, right, e to minus 3t plus the eigenvector times t e to minus 3t. Okay. So that's my answer. Now, I think the book gives some similar answer, who knows? But notice that you could combine things like this. This is actually one single vector. So you can combine them into C1, C2, e to minus 3t plus 0, C1, t e to minus 3t. That could be one way. All right. This and this are both valid. Finally, right, the book likes to present things in terms of the initial condition, in the abstract rather. So they do this, okay? I think text. They take the extra step to say this. Well, the abstract initial condition is this. This is the abstract initial condition. Okay? But what is this in our case? If you plug in the abstract initial condition, right, meaning you plug in t equal to 0, well, what do you get? Well, what you get is clearly C1, C2 in this case, right? So in other words, you can present this one last time as and this possibly is the version that the book used. But for me, 1, 2, and 3 means one and the same thing. They all say the same information as far as general solution is concerned. Any question here? Yeah, as long as it's correct. I don't care which way. And so then, right, B, they say, well, apply it to the particular case when it's going to be 1 and 0, right? So I don't know. I mean, if you have the abstract version of the book, then all you have to do is plug in 1 and 0 here, right? Plug in 1 and 0 here to see what you need. On the other hand, right, if you have my version, I mean, same deal, right? You plug in 0, right? You plug in 0. So if you plug in 0, then you see, right, it's really, again, it's C1, C2, because this is the Pierce. So you got C1, C2 is equal to 1, 0. So that means C1 is 1, C2 is 0. So the particular solution will be, right, e to minus 3t, t e to minus 3t for this problem. Well, you could, but it will be ugly, right? It will be an ugly system. If suppose like, I assume you're asking this, right? Suppose y of t0 is x0, y0. You mean this version, right, Ron? Yeah, and that's why I'm not too big on it, because it doesn't really simplify anything for you. But of course, right, what is this then? It's going to be, right, if you check, it'll be c1 c2 e to minus 3 t naught plus 0 c1 t naught e to minus 3 t naught. Or you get a system, right? You got c1, right, e to minus 3 t naught plus 0, right? So actually here is still fine, but it's still ugly, right? Is equal to x0, and then you get c1 t naught e to minus 3 t naught plus c2 e to minus 3 t naught equals to y0, and you get c1, c2. That's all. So that's why I don't care for like plugging in for C1, C2, plugging in for the initial condition, the abstract ones, right? If you give me a particular set of numbers and a particular t, then I'll just solve for it. But in general, why do I need to, right? This works as good as anything else. So that's that. Any other question? All right. So then moving on, right? So the next thing I want to do is to look at the case, right? Case with multiplicity 3, okay? And the example, right, that we're stuck with last time, or let's look at this, right? So the example one is when we have 1 0 0, 2 1 0, 1 1 1. I'll just recap, all right? This one has, right, 1, right, with as an eigenvalue, with multiplicity 3. So, but on the other hand, it only has one eigenvector, okay, v1. And so in this case, what you do is you solve for two pseudo eigenvectors, right? Where the first one is a minus lambda I v2 is equal to v1. And the third one is the second one, the pseudo eigenvector is this, okay? And we solve for them, with specific values last time, so I won't repeat the calculation. And the solution will be, right, the first, the eigenvector with t squared. And then the second one with t, and then the third one, right, with nothing. Okay, so that's the structure of the solution. So this one, right, is the case when you have multiplicity 3 with only one eigenvector. But what about the case where we were like, at the end of the class last time, right, with multiplicity 3, but two eigenvectors, okay? So lambda equals to 1, 1, 1. But when you look at lambda equals to 1, okay, then you got 0, 0, 0, 2, 0, 0, 1, 0, 0, right? Times, let's say times v equal to 0. Here you have two solutions. let's say V1 is equal to 0, 1, 0, okay, times C1. V2 is C2, 1, sorry, 0, 0, 1. Now, I think on the quiz, some of you wrote down solution for an ODE, even though it's not required, because I'm just asking for, eigenvectors. But I saw a lot of you, when you write down solution, you write something like this, say for this case. Yeah, you can. So you could have this. You could have these two choices. That's also fine, as long as these two guys are independent. So in that sense, 0, 1, 1, and you can have a weird choice like this, 0, 10, and 5, 10 and let's say 11. That also works, but that's super ugly. But as far as eigenvector is concerned, these two choices are also valid, right? Because why? Yeah, so I like this way of presentation, but some people like this, right? Some people just basically write V is equal to 0, C1, C2. And that's actually captured, right? And actually, this way of writing has a lot of virtue here, which I'll explain. But yeah, this is fine too. But you see, because, right, basically the idea behind this is it's a space, okay? Eigenvector is never really meant to be an eigenvector. It's meant to be eigenspace. So what happens is we're saying this is an eigenspace with dimension 2, okay? And up above, we have an eigenspace. Sorry. In this example, we have an eigenspace with dimension 1. All right. Or you might have heard this is eigenvalue with algebraic multiplicity 3, right? But with geometric multiplicity 1. Sorry. Yeah, geometric multiplicity 1. Wait, am I right? What is a geometric multiplicity? Geometric multiplicity, I think, is the number of eigenvectors corresponding to it. So here, this has algebraic multiplicity 3, but geometric multiplicity 2, because it has two eigenvectors corresponding to it. Okay, so yeah, so in general, right, the focus is on the space itself, not on the particular vector. All right, but what I'm trying to address is then some people, right, I saw on the quiz, not required, but you do this. You write C1 e to a t, C2 e to a t. Now, so I think I'm not asking you for ODE solution, so I couldn't care, but I didn't care. But if this were an ODE solution, this is not correct. Or I mean, let's say it's not incorrect, but it's not complete. Okay, because this cannot be the full solution. This cannot be the full solution. This cannot be the general solution. Why? Very simple. When you write down this solution like this, right, just look at it for a little bit and you know it cannot be correct, because you say that the top coordinate must be 0. But that cannot be true, right? The top coordinate cannot be 0, because this is our system. The top coordinate solve for y1 prime equals to y1. So how can it be 0? Okay. So in that sense, this is not enough. So that always signals to us that we need a third vector. Okay. We always need a third vector. So we need one pseudo eigenvector here, which is what we're stuck with last time. Okay, need one pseudo eigenvector. Now, how to find is the question. How to find and how to write a solution. Okay. Because I mean, like what we stuck with last time, right? What we stuck with last time is that this system, right? When you look at this, and this is our general, right, eigenvector. When you do this, 0, 0, 0, 2, 0, 0, 1, 0, 0. Let's say times V3 equals to 0, C1, C2, right? You can see this has no solution because, right, 2 times something is C1 and 1 time that something is C2, right? It has no solution. But let me put a question mark here, right? Because there's something you can say there. And then we have the idea that let's just pick one of them. Actually, that's not a good idea either. Let's say this, right? This clearly has no solution. All right. So the way out is this, okay? The way out, the correct solution is this. The way out is that this system actually has a solution. All right, it has a solution. But what does that mean? So that's why I put a question mark here. This system has a solution as long as you're willing to let C2 and C1 have a particular relationship with each other. In other words, right, this system has a solution as long as, sorry, 0, 0, 0, right? 2, 0, 0, 1, 0, 0. Let's say times V3 is equal to, let me say this, 0, 2, 1 times C1 has a solution, has solutions. Okay? And guess what, right? This guy is an eigenvector itself. This is an eigenvector. Do you agree? So in other words, right, the task of finding the pseudo eigenvector in this case is that you cannot just plug any right-hand side into it. Remember before, right? When you only have one pseudo eigenvector and you only have you have one eigenvector, then you can plug the eigenvector in here and guarantee a solution. Here, there's no guarantee of a solution if you don't pick the right eigenvector. All right, because now you have too many choices. You have to pick the right choice, which is this one. All right, that's the key. So what does that mean then? What that means is my V3 will be, because of the proportion 2 and 1 here, these 2 and 1, they're not arbitrary. They're chosen so that this system has a solution. This is chosen so solution exists. They're not arbitrary that way. Because if you pick any other C1, C2, they don't have solution. Correct. Okay? So they're not arbitrary in that way. They're picked so that I can find my pseudo eigenvector. So I want to say they are not arbitrary. That's the point. You cannot solve for arbitrary eigenvector in this case. But you have to solve for that particular eigenvector only. That's the particular thing about this question. Okay. So you see. So what is my V3, right? V3, right, will be, okay, will be C1, right, times 1, 0, 0. Is that correct? But then I always have to add some stuff here, right? Plus the homogeneous solution. How many, what's the degree of freedom here for my homogeneous solution? Exactly. So you pick up the C2, C3 from here and not from your eigenvector. That's the thing. Okay. You pick up the C2, C3 from the pseudo eigenvector. So in other words, you get C1, 1, 0, 0 plus C2 times 0, 1, 0 plus C3 times 0, 0, 1. That's your, this is your pseudo eigenvector. So what is my ODE solution? My ODE solution will be the pseudo eigenvector, which, by the way, right, don't be surprised, is C2, C1, C2, C3 times e to the t. And then my my real eigenvector, but this one, okay, this one, C1 times 0, 2, 1, e to 2t. Sorry, t e to t. Why is this V3 this way? So first of all, right, this is my right-hand side. So 1, 0, 0, solve for it. Okay, but you always need the homogeneous solution because that's the degree of freedom, right? This system is underdetermined. So therefore, right, there are two homogeneous solutions coming from your eigenvectors above. So that's why you got this one and that one, because they are both homogeneous solution to this system. You plug in that system, you get 0. So this is my YT. All right. Now, this is not covered in any section. This is the extra material I'm covering. So that's why I say this is not on the exam. The reason is, I feel like with the eigenvector structure, right? If I just present to you with like 1 and 1, is too simplifying. All right, things can be quite complex. The eigenvector, can you change C2 and C3? Yes, you can. You can change this too. It's immaterial. You can change this. Yeah. Carl's question. So the eigenvector in the solution is a sum of V1, V2. The eigenvector in here is chosen with respect to this system so that we have a solution. That's why it's chosen based on. It's not a sum or anything like that. It's chosen so that we have a solution to the pseudo eigenvector. Okay. Now, so I will tell you a unified approach later on, okay? But let me tell you this. In case you think this solution is bogus, right? It's just made up from me playing with eigenvector. What is the system? The system is y prime is equal to 1, 0, 0. 2, 1, 0. 1, 0, 1, y. Okay, let me ask you this. Can you solve for this system by yourself? Can you solve for this system by yourself? Sure, because yeah, it's really decoupled, right? It's actually very easy. What does this system say? Y1 prime equals to y1, y2 prime is 2y1 plus y2, y3 prime is y1 plus y3. Yeah, it's super easy, right? In particular, what's y1? Y1 is C1e to a t. Do you see that? And you see why C2 has a 2 here and C3 has a 1 there. And that's why for what's his name? Cheng Hao. Yeah, Cheng Hao, right? He asked if you can switch C2 and C3. You can, because whatever constant free you want to call it. So yeah, right. You see that exactly this solves this system. All right. But somehow from the eigenvector structure is super complex, right? It's kind of like weird, but this is very easy to verify that this is indeed the true solution. So my approach is correct. That's what I'm trying to say, right? On the other hand, right? So I guess some of you might say, why do you complicate stuff, right? Why don't I just solve the couple system? The reason is, of course, I'm just demonstrating an easy system, so we don't have to bother, right? Solving like, eigenvalue, eigenvector. There, in real life, right? There could be a system with repeated eigenvectors that's not decoupled, right? And that's when things get really interesting for you. Okay. So um, before I tell you the unifying approach, any question here for the question? Okay. So let me say this, right? This is not going to happen in this class, but if you care for like systematic understanding of stuff, let me say, right, potential question, right? And then let's suppose you have a 4x4 system, all right? And real life is more than that, right? Let's suppose that you have lambda with let's say repeating 4 times. How many variations can you have? The answer is you can have, well, well, I mean, in terms of cases, right? In terms of cases, I'm having this in mind, right? You have four distinct vectors. That's one case. That's easy, right? 3 eigenvectors, so missing one. 2, right? You need 2 pseudo. And then 4, right? 1 eigenvector. Right? And if anything, you see, with these cases right here, you have to pick how to solve for the pseudo eigenvector in this case can be quite mysterious, or basically how to pick the pseudo eigenvectors here is the question. All right, when you think about it, because just abstractly telling you that a times minus lambda I times pseudo equals to eigen is roughly that, right? But as this problem demonstrate, okay, as this problem demonstrate, you cannot just pick any eigenvector you want, okay? You have to pick the right one. So this calls for the unifying approach, where at least you have a generic structure to things. So the unifying approach is this, all right? And this is just for the math-loving population among you. Not that this is super important for this class, but the unifying approach is like this. If lambda is repeating, okay, there is a smallest, or let me say the smallest power, okay, let me say k. Sorry. There is the smallest power k, so that a minus lambda I raised to a k is equal to 0. Okay? And this is a 0 matrix, okay? And so the solution to the ODE, right, y prime equals to ay, okay? Where lambda is the only, okay, eigenvector, eigenvalue is, okay? Y of t to be, okay, you start out with v e to lambda t plus a minus lambda I v t e to lambda t and then plus a minus lambda I square t squared over 2 e to lambda t all the way to a minus lambda I to a k minus 1. Sorry, I'm running out of space. T to the k over k factorial e to lambda t. Okay, where v is arbitrary. Where v is arbitrary. Okay. Trust me when I say this is actually relevant even for the non-math loving crowd in this class. The reason is that 2 by 2 exactly is this case. Your 2 by 2 can exactly be solved in this case too, as I show you, okay? The 2 by 2 can also be solved in this case. So example, okay? Let me show you example. Let's say problem 5 that we work on today. Problem 5, okay? Problem 5 say y prime is equal to minus 3, 0, 1, minus 3y. Lambda equals to minus 3, right? So a minus lambda I is 0, 0, 1, 0. What I say is find the smallest power k so that a minus lambda I k equal to 0. What is that power here in this example? Exactly, k equals to 2. So what does the structure say? You start out with an arbitrary vector. So arbitrary vector means, sorry, my iPad got stuck. Right, so k equals to 2, right? K equals to 2. So you start out with an arbitrary vector. Arbitrary vector here means C1, C2. C1, C2 e to the minus 3t. And then what, right? Plus a minus lambda I times C1, C2. I'll just do this, all right? So that you see it. But what's a minus lambda I times C1, C2? C1, C2 e to minus 3t plus 0, C1. Isn't that what we got? So you see, you do not even need to calculate eigenvalue. You don't need to calculate eigenvector and pseudo eigenvector in this case. You got it. Question here for this example. Okay, let's take a look at the example, right, that I just wrote. The example 2, right? So A is, I think, 1, 0, 0, right? What was it? 2, 0, 1? No, 2, 1, 0, right? And then 1, 0. Okay, so lambda equals to 1, right? And a minus lambda I is equal to 0, 0, 0, right? 1, 0, 1, 0, 0. Sorry, what am I saying? 2. Correct, Daniel, right? K minus 1, that's why, right? That's why, yeah. So K minus 1 here, right, is exactly that, okay? We can do another trivial example to show you, yeah. But K equals 2 here, yeah. So, right here, what is K? What's the smallest power that you raise it to be 0? Yeah, no, it's not. So sit back, relax, and just enjoy the the discussion, or not. Yeah. So this is t raised to t raised to 1 power, right, Daniel? What's the question? Yeah. So Brett, that's not right. K is equal to 2 here, not 3. 3 is the other case. 3 is the other example. This is only 2. You can check. K equals to 2. Okay. So what is the solution then? The solution is y is arbitrary e to lambda t, and then a minus lambda I times this, right? A minus lambda I times this. So you see exactly. Yeah, actually K is intimately related to how many eigenvectors you have. K equals to 2 here because you have only 2 eigenvectors. You have 2 eigenvectors. K does, K does, K does, as you see real quick. Yeah, because you see this is 2 degenerate. That's why you only need 2, right? We can dial back to the other example. Any question here? And so let's go back to the other one, right? The other one was, what was it? A equals to 1, 0, 0, 2, 1, 0, 1, 1, 1. Okay. Oh no, 4 by 4 is too much, Sagar. You don't want to sit. You don't want to sit there and see me doing 2 by 4 by 4. You can play with yourself, but no, I refuse to do 4 by 4. So here, right, lambda equals to 1. Okay. But when you plug in a minus lambda I, what do you get? 0, 0, 0, 2, 0, 0, 1. Sorry, yeah, 1, 1, 0. Okay. What is k here? What's the smallest power that raised it to be 0? Exactly. All right. And I don't think, I'm already kind of boring many of you enough. I'm not gonna raise it to a 3 power to check, but you can check that raise it to a 2 power will not do it. K equals to 3. Okay, K equals to 3 in this case. So Ron, right? This is exactly what I'm talking about. It depends on how many eigenvectors you have. Okay, the structure are intimately related. So what is the solution then? Remember how before we have to find the pseudo eigenvectors, all this kind of mess, and now figure out the C1, C2, etc. No need here. What is it then? C1, C2, C3, e to a t, and then what, right? Multiply 1 time. I have to be careful here, right? So the top is still 0. Then the second one is what? 2C1, right? Yeah, sorry. So 2C1, right? And then you got C1 plus C2. This one, T to a T. Yes? And then what's the last one? The last one is A minus lambda I squared. Or you just have to do A minus lambda I times this guy. Okay? So what is that then, right? Then I think the top is still 0, right? The second one will be 2. Hold on, am I right? Yeah, the top is 0. And then you got 0 here, and you got what? 3c1 plus c2. That's interesting. Then this one will be t squared over 2 e to a t. You mean here? Oh, hold on. 0, 2c1. I made a mistake, right? Apologize. I can't multiply. It's just 2c1, right? 2c1. Is that correct now? So Daniel, right? Here we're not really in the realm of independent vectors either, and forget orthogonal, right? Orthogonal has nothing with independent. I mean, at least not here. The thing is, right? Remember that we have this one is supposed to be the eigenvector, and then you have the pseudo ones. Remember that? So, but the point is that actually starting with eigenvector and solve it backwardly is kind of awkward. The scheme that I'm telling you kind of start from the forward direction, because a minus lambda I cubed is equal to 0. So that's why you start with an arbitrary vector, and then you go forward, and that's much more comfortable than solving backward. That's the whole trick that's going on here. Okay. Any question? So with this, right, like I said, I can solve all the problem in the textbook very quickly. Yeah, but like basically you reiterate, right? You reiterate and multiply each time. You just do one time, 2 times. But Ron, remember, would you rather do this, or you back solve with an eigenvector and then back solve with 2 eigenvector and back solve with a 2 eigenvector? It's the same thing, right? So obviously, again, in real life, when things get large, you ask the machine to do it somehow. But at least you must have a structure, right? And then you feed that to the machine, right? But if you don't have the good structure, then I guess the machine will also be, right? The code will be super complicated. That's all I'm trying to say, right? In general, K is related to the number of eigenvectors you have. That's all I can say, right? Because for example, here, you have one eigenvector. Here you have 2 eigenvectors, okay? And for this example, right, you see you have 1 eigenvector for the 2 by 2. Let me give you one last example, okay? Or maybe 2 more examples, because this is good to see. Let's say this. Let's take the silliest thing. Okay. Then lambda equals to 1. A minus lambda I is, I guess this is everyone's favorite matrix. What's K in this case? What's K in this case? Yep. So what's the solution? Arbitrary e to the t. But isn't that right? Isn't that the solution? No, Ron. I mean, complex eigenvalues are a totally different beast, right? Complex eigenvalues does not raise to any power equal to 0, right? The reason why you can raise to equal to 0, if you take a higher, linear algebra, right? That's kind of a case only for repeat eigenvalues. Yeah, you have to, but you have to always solve eigenvalues anyway, right? You have to solve eigenvalues anyway. So that's not, I'm not going to save you from that. But what I'm saving you from is calculating pseudo eigenvectors and even eigenvectors at that. You see? Again, right? This is only for repeated eigenvalues, and these repeated eigenvalues are the same. Okay. So if you have like different eigenvalues, like, suppose this is 2, then my procedure doesn't work. Okay. If this is 2 like this doesn't work. Okay. So do not use this with 2, 1, 1. Only when they're all the same. Okay. Only when they're all the same. Lambda is the only eigenvalue, then that works. Okay. But this is safe to use for 2 by 2. All right. For 3 by 3, you must have a multiplicity of 3 before you can use this. So will you have a question of why this is arbitrary? Because the procedure always tell you to start with an arbitrary vector, right? Start with arbitrary and then go forward until you meet k minus 1. But here k minus 1, right? K is 1, 1 minus 1 is 0. So this is where you stop. Yeah, no. Any other question? So I guess maybe let me also show you problem 7 in the book. Okay, under this new lens. This is like a compensation for people who kind of have to wash through this. So problem 7 from the book says y prime is equal to minus 2 minus 1, 1 minus 4, right? Y. So what's the eigenvector? That's the only thing I need to know, right? So I got lambda minus 2, sorry, minus lambda, right? So 2 plus lambda times 4 plus lambda, right? And then minus 1, so it becomes plus 1 is equal to 0. Am I right? So I got lambda square plus 6 lambda plus 9, right, equal to 0. So lambda equals to minus 3, repeating. Okay. So lambda equals to minus 3, repeating. So a minus lambda I is equal to 1 minus 1, right? 1 minus 1. Guess what k is in here? K equals to 2, right? A minus lambda I squared is equal to 0. Can you see that? So what's my solution? Y of t is C1, C2, e to minus 3t plus C1 minus C2, C1 minus C2, t e to minus 3t. I think this is the right solution. Can anyone verify with the book? But anyway, right, see how beautiful that is? I don't even have to solve for eigenvalue, eigenvector. I don't have to solve for eigenvector and pseudo eigenvector, right? I still have to solve for eigenvalue. K is the smallest power so that a minus lambda I squared is equal to 0. 0 matrix. Sorry, raised to k power. Okay. Most of the time, for the truly like pseudo eigenvector case that you found in 2 by 2, k is equal to 2. All right, but do not rely on that. All right, if you use this method wrong, don't blame me, because there are examples when k equals to 1, like this. So right, it depends. It depends, but I can tell you with 2 by 2, most of the time you see k equals to 2, right? Most of the time. So that's the quickest way to write down the solution for 2 by 2. But right, do yourself a favor and make sure that really you square this, you get 0. Okay. How do you figure that out? You try power, Lauren. Like you try 1, doesn't work. You try square, it works. Then that's it. Yeah, exactly. Absolutely. Yeah, exactly. And by the way, right, k cannot be larger than the dimension. Okay, k must be at least the dimension. So at most the dimension. So if 3 by 3, at most 3, that you're right, exactly. So for 2 by 2, it's only 1 or 2. 2 is the hard way, is a hard case. 1 is the easy way, like Daniel pointed out. So here I can solve 6 and 8 for you like in 2 minutes, right? All it takes is just to figure out eigenvalue. And by the way, right, in case you're curious, there's no secret to this. This is just basically reverse everything, right? Instead of starting with the eigenvector and then solve back for pseudo eigenvector, right? I start with the arbitrary one and then move forward. Any question? The book might mention it. I don't know. Does the book mention it? I have no idea. I mean, I know the method. I just teach it. I know too many methods. I don't even know what method the book teaches. But maybe, right, you can ask, why don't I teach you this at the beginning, right? Because I feel like if I teach you this at the beginning, then the structure of the problem doesn't register with you. And also the pseudo eigenvector approach, right, has its merit. The whole concept of pseudo eigenvector is useful, right? Be very careful of just falling in love with particle approach and then forget the idea behind things, right? I feel like the idea behind things are still pseudo eigenvector approach. You can use whatever method you want. Again, for me, right solution, I don't care. But I warn you, if you use the wrong method and you get a wrong answer, or you use the method at the wrong time, that is on you, right? I present you all the tools you need, you get to choose, okay? But yeah, so my emphasis, right, is you want to understand the idea behind the method, right? So that you apply it right, that's all. Right here, Rumin, I show you with these examples. And then, with the one above. But again, right, this only works if you have all repeating. If you have some, like 2, 1, 1 like this, mine doesn't work either. So this is only fast if you have to deal with, if you have really everything repeating. But if it's break in between, then my method has to be modified. And that's when it's really get complicated. So I don't want to discuss that. Okay, so sorry for spending so much time on this kind of thing, but it's really fascinating with a lot of angles. So next week we're gonna just do the graphing, and then we'll move on to new material. Okay, so this is the last thing I want to say about analytical solution for repeating. All right, thank you. Thank you. Tuesday, Thursday, 3:30 to 5. So I have an office hours right before our exam on Thursday. Yeah. You too. Mhm. You do. I can repeat it. Oh, graphing, no, you won't need to do graphing, right? But you still need to do analytical solutions where you have like two repeating, yes. But no graphing. Graphing is only for complex and separate, because I haven't covered the graphing for the repeated case, yes, yet. Okay, yeah. All right, sure. See you then.